Hello everyone, and welcome back to Total Organic Chemistry. This video, I will be discussing electrophilic additions to alkenes, as well as their halogenations. By the end of this video, the questions that you should be able to answer are: how does the pi bond in alkenes react? How do electrophiles functionalize alkenes? How can I synthesize haloalkanes from alkenes? And how are these reactions stereo and regioselective? If you'd like some quick review on the properties of alkenes, or a couple simple methods to synthesize them, please go ahead and subscribe, and also take a look at my videos on that. The main concept of this video is that the extra electron density in the pi bond of alkenes makes those alkenes nucleophilic. So if we have an excess of electrons, we can donate those electrons to a nucleophile, and depending on our choice of nucleophile, we'll get a wide variety of products. So let's jump right into a reaction here. We can take propene, which is our 3-carbon alkene, and treat it with a halogen acid. So I'll just write HX, and this reaction works best with hydrochloric, hydrobromic, or hydroiodic acids. So hydrofluoric acid is generally not very great for this type of reaction. And this will add to the alkene in a fashion that gives us the haloalkane, where we have the halogen added to this secondary carbon here. Let's take a look at the mechanism. We start with our alkene, and because these are strong acids, we'll have some sort of H+ floating around in solution. And while we know that H+, just a proton, is never by itself in solution, that is, it's always bonded to something, we can just write H+ here for simplicity. And because of this extra electron density in the pi bond, we can draw those 2 electrons in the pi bond coming to attack the proton and form one of 2 intermediates. We could get this intermediate here, where we have that proton bonded to the primary carbon of the double bond. That would give us a secondary carbocation here. So we'll write that plus charge because we no longer have that double bond, and that will be electron deficient right now. Adding the proton to the other center will give us this intermediate, where the hydrogen is on the secondary carbon, and we have this primary carbocation. And you should remember from my video on carbocation stability that this secondary carbocation will be much more stable than the primary one. So this is going to be the intermediate that forms, and we'll take this for the next step of our mechanism. This secondary carbocation, again, has that positive charge, so now our nucleophile in solution, the bromide, Br-, can come to capture that carbocation, giving us the secondary haloalkane as a product. This is our first example of Markovnikov's rule, which we'll see a lot in electrophilic additions, which means that the electrophile will bond to the more substituted carbon. So we call this a Markovnikov addition because this secondary carbocation is more stable. The more substituted carbon will be capturing that nucleophile in the end, the bromide. If we look at this alkene, trans 2-butene, and we treat this with maybe hydrochloric acid this time, we can have the same first step where that pi bond will come to attack the proton, leaving us with a secondary carbocation here. And remember that carbocations have planar geometry, so this chloride that comes in to capture the carbocation can approach from either side, either above or below the carbocation, giving us a racemic mixture of 2 products. So we'll have one product where the chlorine is coming out of the page towards us, and the other product where the chlorine is going into the page. So we'll have that racemic mixture of 2 enantiomers. Let's do one more example where we look at this substituted alkene, where we have just a mono-substituted double bond, and when we treat this with hydroiodic acid, HI, we might expect to get this product, where the alkene has turned into an alkane, and we've added that iodine to the more substituted carbon, so the secondary carbon in this case. However, we also know that because this mechanism involves a carbocation intermediate, we can have rearrangements occur. So if you need some review on carbocation rearrangements, take a look at my video that's linked at the top of the screen. And what that means is that we will actually get a rearrangement to give us this product instead, where we have a hydride shift to give the iodine on the tertiary carbon here and not the secondary carbon. So that is an important aspect of this reaction to keep track of because we know that we have carbocations involved. What if we wanted to add the halide to the other carbon, so instead of the more substituted carbon, adding it to the less substituted carbon? Well, again, we can take propene, that 3-carbon alkene, and treat it with hydrobromic acid and an organic peroxide. So I can just write ROOR, where that peroxide bond is the oxygen-oxygen single bond. And this reaction really only works very well with hydrobromic acid and actually not any other halogen acids. And this will give us the primary haloalkane this time, where we have that bromine bonded to the less substituted carbon. We call this an anti-Markovnikov product because this is again the less substituted carbon, whereas the Markovnikov rule tells us it would be the more substituted carbon. This reaction proceeds this way because organic peroxides are very good radical initiators. So what that means is that our oxygen-oxygen single bond in the organic peroxide can be broken homolytically, not heterolytically, using either heat or maybe light to produce this radical species here, the RO dot. And this is similar to the initiation step we encountered in radical halogenation of alkanes. And if you'd like some review on that, again, take a look at my video at the top of the screen. This oxygen radical can abstract a proton from our hydrobromic acid, again breaking that bond homolytically, giving us the bromine radical, as well as the alcohol as a side product. And now this bromine radical can attack the alkene, where that pi bond in the alkene will again break homolytically to capture the bromine, as well as form a radical on the alkene carbon chain. And in this case again, we want the more substituted carbon to hold the radical, because just like carbocations, the secondary radical here would be more stable than the primary one. So this secondary carbon radical can again abstract another proton from the HBr to give us the haloalkane product, as well as regenerating that bromine radical. Finally, maybe as a termination step, we could have two bromine radicals coming together to form a bond to give us just elemental bromine, and there could be a variety of other termination steps as well. Let's look at a final type of halogenation reaction where we can actually make dihalides. So again, let's just start with our very simple alkene propene, and treating this with elemental bromine will actually give us what we call a vicinal dihalide. So where these two bromines have added across the double bond, and dihalide because we have two halogens, and vicinal meaning neighboring carbon atoms. As always, let's take a look at the mechanism. So we start with our propene, and we also have the Br2 molecule, so that's just a single bond between the bromines, and because this bromine-bromine bond is relatively weak, we can have the alkene attacking this bromine here. At the same time, another one of the lone pairs on the bromine atom will attack the other carbon of the alkene, whereas the bond, the bromine-bromine bond, will swing over to the other bromine atom to form our Br- anion. So what we end up with here is what we call a bromonium ion, where we have the three carbons from the alkene structure, and then we have a three-membered ring with bromine in it, and that bromine will carry a positive formal charge. So you might be asking, why are we forming this bromonium ion, this ring, instead of just forming a carbocation like we did in the previous reaction? Well, if we draw a resonance structure for this bromonium ion, we can see that we also have this contributor, where we no longer have that positive formal charge on the bromine, and rather we formed this secondary carbocation. So although the carbocation might be more familiar to you, because the bromine is such a large atom, it can actually accommodate this three-membered ring and those multiple bonds. So because the carbocation is a sextet and the bromonium ion is an octet, the octet will actually be more stable, and the bromonium ring will probably be the most stable resonance contributor. This might also be reminiscent to you of our reactions of epoxides. Our nucleophilic ring openings, catalyzed by acid, also have this three-membered ring with a positive formal charge on the heteroatom. So in epoxides that would be on the oxygen. In this case it is on the bromine atom. This reaction will be very similar to that. So we have a nucleophile in solution. We have this Br- that we produced last time. And just like in our ring opening reactions of epoxides, this bromide will come in and attack the more substituted carbon, opening up the ring and giving us the final product, the dihalide, where we have one bromine attached to each of the carbons of that double bond. We can perform the same reaction with chlorine. So let's start with cyclohexene as our starting material alkene, and treating that with Cl2 will give us this product here, where we've added the chlorine across the double bond. The first chlorine will be coming out of the page towards us, and the other one pointing into the page. We'll also get the enantiomer of this because this has generated new stereocenters. However, in both cases, we will obtain the trans products and never the cis product. The halogens have been added on opposite sides of the double bond because the formation of that halonium ion and the subsequent attack from the opposite side of the ring gives us always anti-addition in these reactions. So again, anti meaning on opposite sides of the double bond. Another tool we can use in tandem with these reactions is that those halonium ions, so the bromonium or chloronium ion, can be captured by other nucleophiles and not necessarily the same halide. So if we take cyclopentene and treat it with Br2 in water, we can actually form what is called a bromohydrin. So instead of the dihalide, we'll have the bromine coming out of the page, and then on the adjacent carbon, we'll have a hydroxyl group, again going into the page from that anti-addition we just talked about. Let's draw out a mechanism for this to see how it works. Again, starting with the cyclopentene and also the bromine molecule. We'll have the pi bond in the alkene attack this bromine here. And just like before, we'll have the other lone pair on that bromine attacking the other carbon. Finally, this bromine-bromine bond will swing up to the other bromine to form the Br- ion. That will give us our bromonium intermediate, and I'll draw that with the bonds coming out of the page to show us that that bromine is above the plane. And because we have another nucleophile in solution, so not just the Br- that we generated, but also using water as a solvent, we can have the water come in acting as our nucleophile to open that ring up, which will give us this protonated alcohol, again having the hydroxyl group into the page instead of on the same side as the bromine. And then we can deprotonate this alcohol, maybe using another molecule of water, because that's our solvent again. And that will give us the final product, the bromohydrin, with the bromine and the hydroxyl groups on opposite sides, so that anti-addition that I talked about. And if you're extra astute, you'll notice that we'll also form the enantiomer of this, because upon formation of that bromonium ion, it could be on either side of the alkene, so that means that we could form either enantiomer, and we will form a racemic mixture of both in this reaction. And when using other nucleophiles in addition to just the halogens, we will have the other nucleophile, so in this case the water, adding in a Markovnikov fashion. So if we had a more substituted alkene, we would have that water adding to the more substituted carbon, and the bromine would add to the less substituted carbon, because of the ring opening reaction that proceeds in sort of a pseudo SN1 fashion. So I hope this video helped introduce you to electrophilic additions to alkenes and how to halogenate them. If you liked this video, please like and subscribe to my channel. Like me on Facebook and check out my website on the screen. If you're willing, please consider donating to my Patreon page, which helps me to continue creating these content for all of you. Thanks for watching.